So we're going to do an example of the longitudinal dynamics, calculating the denominator polynomial. And this is an airplane similar to airplane G. It's a bizjet. It's in a cruise condition. And it's in a table, not in the back of the book, but on page 330. 330. I was thinking that's a 6. Let me double check. Yeah, page 330. So if you have your book, you can look at the data. Otherwise, I'm going to put it up on the screen. But what we're given in that table are the non-dimensional derivatives. And these are the same as what you see in the back of the book in the appendix. You're going to get stuff like CL alpha, CMQ, etc. Because that's what you estimate when you're doing a preliminary design for an aircraft. So we need to calculate the dimensional derivatives. And then the characteristic polynomial coefficients, the A1, B1, C1, D1, E1. And then we're going to calculate the roots of the polynomial and look at the different modes. So get out your calculators, because I'm going to give you the formulas and the data, and you're going to calculate. Now we'll do just a couple examples of these. We'll just do one dimensional derivative to show you how that works. And then we'll calculate A1, B1, C1, D1, and E1. Actually, we do the first two. In the upcoming homework set, you'll do the next three. So let's start with that. The XU formula comes from that table in the book that shows the dimensional derivatives. And that's in your handout that I gave you. It's like page 2 or page 3 in that handout. Page 3. So either look at that handout or copy this down in your notes, because then I'm going to switch to the page that has the values that you need. Okay, so XU so mass is weight divided by gravity. That's how we'll get that. And then here's U1. So everybody copy that down. See if I can get it to focus better. Yep, that worked. So are we good on the formula? Or you have the sheet from your handout or your book? So here's the data. I'm going to zoom in so you can see this better. So you need the forward velocity 400, the wing area. Yep, we need that. Need the dynamic pressure. Need the CD1 and CDU. Notice I've highlighted them in yellow conveniently. So punch away and see if you get this value down here, because this is what we're calculating, is the XU value. So this is our target. Sorry, you need CDU over here is 0. So how are we doing? You got the numbers substituted in yet? And then punching through. CDU is 0. First spot check, what are you doing with the 400 knots? Yeah, so what do you get for that? 675? Is that right? Yeah, I got 675.12. Just double check that. That's a good reason why you should always look at your units, right? Because here they are giving you it in knots, and you don't need that. And he's got a, where's the weight? It's up here. The what? The units what? Yeah, what does it say on that page with the are you just looking at that? You're saying, yeah, so we need to validate the units on that as well. You got 0075? And that's what I get, is I get minus 0.007529. Anybody getting 0074? You're getting what? Okay. And every year I ask this question because I never can figure out how they got 0074. Because the knot conversion is accurate. I mean, gravity is 32.2. Am I rounding that off? What is gravity? Out to like 4 digits. 32.2. 0.19178. Yeah, and I think we've even put that in, and it doesn't make that much difference. So I think there's just it's just slightly off. It's off by like about 1%. Okay, so we're all in agreement. And did you work the units on it? Let's look at those. So let me switch back to the board here for just a minute. So we should double check our units because that would help us avoid putting in knots by mistake. So we've got this, which is the pressure, pounds force, foot squared. These are dimensionless. And here we've got mass, so we've got slugs. And here we've got feet per second, assuming we did the conversion, which this would have told us we didn't do it if we had a problem. And so then a pound force is a slug feet per second squared. So the slugs cancel out. And I'm not sure what. Oh, it's just my feet were messed up, and that's why. Right? It's dynamic pressure. That makes more sense. So then this cancels with this. That cancels with that. Thank you for saving me there, whoever said that. The seconds, one of those cancels, and we get 1/seconds. And that's what the chart, the table says that it should be. And again, the value I get for this, and we've validated that, is minus 0.0075. All right, the next step. Now, again, you'd use the same process to calculate all the needed dimensional derivatives. There's a lot more than this. But we're going to use the values that he's giving us in the table, assuming that we can all punch numbers. And so now we need to calculate A1. So we look in the book and in your handout, and there's the formula for A1. So let's do that one. So everybody write that formula down, and then I'll go back to the numbers because we need Z alpha dot. I'm assuming everybody got that written down because it's short. So Z alpha dot is here. And then we need the 672.12 for the forward velocity. So that's easy. So you should get 675.99. And then we're going to need the formula for B1. So I'm going to write that on the board and let you work on that. Everybody good so far? You got 675.99. Notice that you're adding 675.12, the forward speed, to Z alpha dot. And right away, you could almost say, well, we can neglect Z alpha dot in that formula. So there's approximations you can make along the way that help out with some of these calculations. Okay. Back to the board. So I'll write up here, notice this is small, and you can't just say small, you have to say small compared to that. I want to calculate B1. More accurately, I want you to calculate B1. So you can look in your handout in the book or on the board here. dot U1 ZQ. Yeah, so we're good. So let's calculate this. And make sure you do some intermediate answers, like do this all as one chunk so we can double check that. Well, of course, we'll know what that is. Do this as a chunk so we can double check that intermediate calculation. So let me give you the data now, as soon as everybody's written that formula down.
Where are you getting these formulas
from? The book and your handout. If you flip back to the last page or the second to the last page, they're listed there. It's the stuff that goes into the denominator D1 bar. And those are just copied from your book, so it's in there as well. And remember where these came from. They came from Cramer's rule, determinant of the A matrix for the 3x3 matrix problem that we solved. Good question. Whenever we're doing something, you should always think back, well, where did this come from? Where did this come from? Why are we doing this? Somebody says, jump in a car and drive to California. You should say, okay, why am I doing that? And they'll say, to go to Six Flags Magic Mountain, and you'll go, okay. That's in LA. All right, everybody got this formula? I'll go back to the data now. So again, the fundamental reason why are we calculating these? Because we're going to get the roots, which are going to tell us whether it's stable or not and whether it's oscillatory or not and how oscillatory it is, which is important if you're the pilot of the airplane. Speaking of which, do we have people in here that are pilots? You are. Oh, I thought you were. Anybody a pilot? Like, you're a pilot? We've got some pilot displays that we want evaluated by subjects. If you're interested, see me. It'll take about an hour of your time on a flight simulator, not in a real airplane. Let's see where, okay, we're going to go now back to the numbers, right? So here's the numbers. You need Z alpha dot, XU, XTU, MQ, Z alpha, M alpha dot, U1, and ZQ. Does anybody see a slightly shorter way to do this than brute force all the numbers? What's the first term? Yeah, the U1 minus Z alpha dot we already calculated. That's A1, right? That very first term. So you can save a little bit of time. I've said it before, but as an engineer, you want to be lazy, but you want to be smart lazy. You look for more efficient, but still accurate ways to do stuff.
You get 9 million?
Get what?
3 million?
3 million. I get 1,359.43. So if you guys have numbers written down, I'm going to switch back to the board and we can put intermediate answers in. Anybody? Still? Yeah.
1359.43.
That's what I got. Anybody else getting that? So we're good. Can I switch back to the board? So the numbers that feed into that, when you do this thing here, you should get 640.23. Of course, this is just a number. This is 445.724. And this thing is 273.98. Which is pretty close to the conversion from degrees Kelvin to degrees C, right? Don't know why that is. And so I get 1. And the numbers that go in here, this is 0074 with a negative sign. This is 0. This is 0.9397. That number goes in as a negative, so you get a negative and a negative. This is minus 0.4062. U1 is big here and ZQ is small, so we really could neglect ZQ as well. So you see how this works, right? You just plug numbers in. In fact, if you had to do this 10 times in a row for different numbers, you'd probably write a MATLAB program or an Excel spreadsheet to do this, where you just put the numbers in. You can change your values going in. In fact, you might even want to start with the dimensionless derivatives and have the code to calculate all the dimensional derivatives automated, which is what he did in this textbook. He wrote code to do this. All right, in homework, you're going to do C1, D1, and E1. So I'm just going to give you the numbers. So that means that the polynomial, the characteristic polynomial, which is the denominator of those transfer functions and gives us the roots that we need to look at, has these coefficients. So A1 was 675.99, and that's what multiplies S to the fourth. And there's B1. So it's a fourth order polynomial, so we're going to get 4 roots. And the easiest way to do that is to use MATLAB. And literally you type in a vector of it's an array that contains the coefficients of the polynomial, and then you say roots. I'll show you a screenshot of that. But the roots we get are this set, two complex conjugate pairs. In 607, do you study the Routh stability criteria? Do you remember that? So one of the criteria is that all of the coefficients have to have the same sign for stable, and we satisfy that, and then you have to do the Routh array. So there are computational tools that they developed before computers could do this kind of stuff, calculating the roots, to give you an idea of what the stability was real quick. All right, so we get these two sets of roots, and here's how you do it in MATLAB, unless you guys already know how to do that, right? From 227, but I'll remind you. 10 years ago. So in this chart, they give the denominator polynomial, so we can check our answers here. So that's the polynomial. And notice this is the elevator to speed, speed to elevator. This is factored, so it actually shows the complex conjugate pairs of roots. This is the angle of attack to elevator transfer function. And then down here is the theta to elevator transfer function. So there's three transfer functions because it's a 3x3 problem solving for u, alpha, and theta. But this is all the stuff we just did. In MATLAB, here's how you do the roots. You create an array, P. I chose P because it's a polynomial, but it doesn't have to be P. It could be your first name, your last name, or your pet's name. Say P equal open bracket, number, 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 number. Those are the coefficients of the polynomial, but they're just entered as an array. And in fact, you don't have to put the commas in there. Close bracket. And then you hit return and it spits out that array. It's just an array of numbers. But when you say roots, then it says, oh, okay, that array are coefficients of a polynomial, and I'm going to calculate the roots of that thing. And so there's the two sets of roots that we get. And there's a theorem in algebra that says if all of the coefficients of a polynomial are real, then the roots will either be real or complex conjugate pairs. So you always get this. Now what do we do? Go home and watch a replay of one of the NFL games from the weekend. Or maybe we should analyze the roots first. I definitely don't want to watch any more election news. I'm done with that. So there's two sets of roots. And we look at this one, and this is the real part. So we'll call this n. And this is the imaginary part, so that's omega. For this set, in fact, we could call this n1, and call this n2 for the second root. And remember, this is the number here. So what does this mean? This means we look at the real part and we go, oh, negative. So it's stable. And we say, okay, it's got an imaginary part, so it oscillates. What's the frequency? Omega. 2.65 radians per second. And it has to be that way because the response of this thing, when you inverse Laplace it, if you did that, this goes into the e to the minus nt, And this goes into sines and cosines. There may be a phase shift here, phi, but you get 2.65 t. And so that has to be radians per second because the number times t has to be radians to go into the cosine. And it is. How about this one? We look at that, we go negative real part, stable, imaginary part, oscillatory, frequency is 0.0919. So we can even go farther than that. Which one is more stable? The top one? Because it's a bigger negative number, right? So the e to the -1 is going to decay much faster than down here. E to the minus 0.0042 t. Which one oscillates faster? Top one, higher frequency, it's going to wiggle faster. Lower frequency, so higher. We could even say more stable and less stable, comparing the two together. And these kind of roots keep appearing for normal airplanes in a standard configuration. So people gave them names. And the names that most people use for these is that this is called the phugoid, which is really just Greek for motion. And that was the first mode that they observed in flight because it has a low frequency, so it has a long period, so they can actually feel it happen. And it's lightly damped, so it stayed there for a long time. So they could observe it. So they called that motion. And then they found this one, and it has a higher frequency, so the period is shorter. So they called this the short period. Again, these are just common names that everybody uses so that they know which mode you're talking about. And for some airplanes, I'll show you a jet fighter, you don't get this standard set of named frequencies or named modes. And so if you're building your own airplane and you get a different set of routes, of modes that don't match this, you can name them whatever you want. But most modes for most common airplanes have been named already. So that took some work, right? We had to take the differential equations for u dot, alpha dot, q dot, and theta dot. We had to Laplace them. We had to take all those 3x3 determinants. We had to put them into the formulas for Cramer's rule to solve, get the denominator polynomial, calculate all those coefficients. A lot of work, right? 2 days worth. And then we had to calculate the coefficients, then we have to use MATLAB or some other root finding method to find the roots to get this. So that's method one. Method two is to put it in state space form. Which, remember, looks like that's a matrix. You get all the derivatives only on this side. Then you get another matrix or a vector times the input. And in this case, it's just delta E, so it's not really a matrix, it's just a vector. But this is typically written in the form where X is called your state vector. And although you probably ought to put a vector on it, it's just an array. It's a vector of numbers. And then this is x dot, because that's what we call x. So there's nothing magical about this. We just call that thing the state vector, and we call it x. You could call it, again, anything you want. But then this formula, state space form, as long as you know your A matrix and your B matrix, and we call this U the input, as long as you know those two matrices, that tells you everything you need to know about your system and the dynamics. Because you wiggled the equations around and massaged them into fit into this exact form. And from that point, we don't need to Laplace, we don't need to calculate A1, B1, and Kramer's rule and all that. All we do is find the eigenvalues of the A matrix. Because, like I said, once you put it in standard form, we know the answer. And the answer is that the roots of the characteristic polynomial for a system in state space form are the eigenvalues of A. And I'm going to show you why that's the case. But that's a lot faster, right? You simply take your state space form, which has all those dimensional derivatives in it, you pop the numbers in there, you feed the matrix to MATLAB and tell it to calculate the eigenvalues. So you got to feed A in, but there you go. But of course, you need a computer program to calculate the eigenvalues of that matrix. If you had to do it by hand, it would probably take as much time as doing all the other stuff, the other method. So this method is newer because for big systems, you need a computer to calculate the eigenvalues. Although there are methods to do that by hand as well. All right, so here's how it works. I said you don't have to Laplace. It's because it's standard form. We already know the answer. But the proof of this, it's not really a proof. It's a demo. So let's take the Laplace of that thing. It's differential equations. Just like we did before, we can Laplace each of these equations. So the Laplace of u dot is s times u, right? The Laplace of alpha dot is s times alpha of s. Same for these. And so it's just s times x of s. So we get s, where we have to say, okay, we're going to call the Laplace of these variables, the Laplace, we're going to call that x of s. Right, so really behind the scenes, you're Laplacing each equation by itself, but then you stuff it all back into a matrix, and so we can just write this down. And A is just numbers, so we know that Laplace of a number times a variable, you just pull the numbers outside, right? So we get A x of s, so that's the Laplace of the x vector, which is just u of s, alpha of s, q of s, theta of s. B is a set of numbers. Whatever u is, the input vector or the input values, that's a time function. So now the process is you Laplace and then you solve for x, right? Forget the state space form. If we were going to solve these equations, you'd Laplace them, you'd solve for the variables algebraically, and you're done. So let's put all the x's over here. Because we're going to solve for x. And I want to factor the x out, but I have to be careful because s is just a variable and A is a matrix, but I can write this as S times the identity And then it becomes a matrix that I can add to A. And I haven't changed anything because this is S times each of the terms in that column. And that's exactly what you get when you take S times the identity. Everybody good so far? So all we did was take state space form, Laplace it with our normal methods, and then solve. We're still going through all the steps, but the answer is going to be standard. So what's the next step here? You can either multiply by the inverse of this thing on both sides, or you can apply Cramer's rule. Either way, you end up with a polynomial up here. That's the stuff of B. And then you get the determinant of SI minus A in the denominator, because that's what Cramer's rule says. If we use Cramer's rule, we replace one of the columns in that matrix by the right-hand side, right? But in the denominator, you always take the determinant of the matrix. And in fact, that is exactly the roots of this thing. The roots of this polynomial are the eigenvalues of A by definition. Because if you go back to your math class, an eigenvalue is you take the matrix and you take SI minus that matrix, you take the determinant, and those give you the eigenvalues. So it's not magic, it's just that the math people have already defined this eigenvalue thing that we know how to calculate, and it turns out when you take state space form, you get the eigenvalues as the roots of this denominator. So that's why people tried a whole bunch of different ways to come up with a standard form for this, because they got tired of doing the same thing over and over again, the Laplacing, putting it into a matrix, solving it, partial fraction expansion. And somebody came up with the fact that say, hey, if we put it into this form, then the solution looks exactly like this, and the eigenvalues are the roots, and we're good. So that's the advantage of state space form. The other advantages, like I said, is you can go into MATLAB and say, here's my A matrix, here's my B matrix, give me the time response of X, and it'll do it for you because it's a standard form, and somebody's written a program to do that. So that's why I'm having you do the state space form in addition to the method presented in the book, is because in the next homework, you're going to plug numbers in and show that you get the same roots either way. And you'll see that the state space form is pretty slick. It's fast. How are we doing on time? 4:59. All right, so we've looked at the roots, and we said, well, this one's stable, this one's oscillatory. To look at those in a standard way, we want to put them into that standard second order form. And so that's why in a lecture a couple class periods before, we did that. We said, what if we have a standard second order form? How do we calculate the damping ratio and natural frequency from the roots? So what we're wanting to do is to put the modes into that second order form, which is S squared plus twice the damping ratio and natural frequency plus the natural frequency squared. And we had formulas for this. We have omega is the square root of the real part and the imaginary part squared. And the damping ratio is the real part divided by that natural frequency. So this was lecture 2 days ago, something like that. So if we do that for the short period, this is the real part, this is the imaginary part. So that's an easy calculation once we have the roots. And then the damping ratio, SP stands for short period. Real part divided by that number we just calculated. And then we can go back and say, we analyzed how the damping ratio affects the response. Remember that? If the damping ratio is greater than 1, the roots are all real. If it's less than 1, then it gets oscillatory. If it's 0, it's undamped. So we can look at this and go 0.353, that's definitely less than 1, so it's oscillatory. Well, we knew that. But it's not super well damped because it's not near 1, but it's not horribly damped because it's not near 0. So it's decently damped. We can say, I spelled decent right? There's no S? That comes from descent, I think, yeah. Yeah, you're right, okay. But is that good enough? We don't know. And that's where chapter 6 comes in, is it will tell us what do the federal aviation regulations say this damping ratio should be for good pilot handling qualities. So we'll get to that, but we'll need this number. And then for the fugoid, we do the same calculation. Plug in the real part and the imaginary part, which is the frequency. The natural frequency is 0.092, which is the resonant frequency, if that means anything. And usually what we're most interested in is the damping ratio. Although the specs on some of these modes do say, well, it has to oscillate below a certain frequency. And so we look at this and we say, okay, that's a damping ratio that's getting down close to 0, so it's not very well damped, which fits the fact that the real part was pretty small. But this puts it on a scale of what we know from 0 to 1 for damping ratio, and you can say, yeah, that's pretty close to 0, so this is not well damped, and this is decently damped, or whatever that means. So if we did this process for another airplane that's a jet fighter, go through all the calculations, get the roots of the denominator polynomial. He shows you these in the book. So this is on page 332 for a jet fighter. You get a root that's plus 2.90, one that's minus 3.59, and we want to name them. And we want to say, well, what's stable and what's not stable? So what do you think? The top one, stable or unstable? Bad, right? Positive real part, unstable. It's not oscillatory, so it just diverges away. How about this one? Stable? For sure, right? How about this one? Stable, but kind of barely, right? And this has a free, so it's oscillatory because of that imaginary part. And it's a low frequency compared to the numbers that we saw before, right? It's kind of on the same order of magnitude frequency-wise as the fugoid mode. So we would probably call this the fugoid. Why? Because it's lightly damped and it's oscillatory with a long period. So it's not a short period. So we classify it as long period. What do we call this? It's not a short period anymore because there's no oscillation. So we make up whatever name we want for it. We could call it a degraded short period. Or we could call this the nice root mode, and the bad root mode. So how does the jet fighter fly? It looks like it's dynamically unstable. That's got to be hard to fly, right? So they sacrificed stability for supersonic flight performance and other maneuverability. They put a delta wing on it so it could go supersonic, but it's unstable. So would you fly it? You would? Just jump right in there and take off. It starts going like this, and then you crash into the ground. So how does this thing fly? This what? Say it again. It does something for you, or automatically does like control deflections? Yeah, in fact, this is where 607 comes in. They put an output feedback controller to stabilize the airplane. So they get the aerodynamics right for supersonic flight, and then they fix this up. They add a feedback loop with sensors directly into the elevator deflection. And as the airplane starts to try to pitch up, the flight control system pitches it back down and stops it. So it adds artificial damping. And you learn how to do that in 607, right? How to tune a controller, how to put a PID or a proportional integral or a phase lead or a phase lag controller. And you pick the constants in the controller to fix these kind of problems so that the closed loop system has good behavior. You guys have all done that yet? You're all laughing like, yeah, we think we've done it. Yeah. And it works. I mean, you put this system transfer function in a block, you put a controller in front of it, you close the loop, and then you have to do the algebra right to get the overall transfer function. And then you choose the parameters to make the roots of that closed loop system behave like you want them to, hopefully. Anyway, that's beyond the scope of this class. So the next part that we're going to talk about is approximations. Either way, state space or the full set of equations, it takes a bit of time to calculate these modes. So there's approximations that people have come up with that shortcut that process. And it's some of the things like we talked about, you could say, well, this term is small compared to that one. It turns out for some of these modes, some motion is less than another motion. So I want to show you that, and we'll do the approximations next time. But there's a simulation that I've done. And what do I want to show you first? Let's see. Yeah, so what we need are the polynomial transfer functions on that one chart. So go back up to this page, and we're going to grab, see if I got a thing to draw. We're going to grab this transfer function. So this transfer function here is the U of S. We'll see how well this goes. To delta E of S transfer function. So in the Laplace domain, that is this polynomial ratio. And then down here is the same thing for alpha of S. And then down here is theta of S. I'm not doing the denominator because I'm struggling to write. So this is theta of S to delta E. So if we take this transfer function and we multiply it by whatever elevator is, like a step input, then we can observe, after partial fraction expansion, we can observe the motion of U of S. So one way to do this is to go into MATLAB Simulink, and Simulink can take these transfer functions and solve them for you and show you the results as a function of time. It's pretty slick. Have you guys done anything in Simulink? So I think I'll walk through, I'll show you how this works. Because Simulink is real slick when it comes to simulating time-dependent functions. So I need to get this over here, these 2 pages. So the first thing you do is launch MATLAB. I need to get rid of this. There's our transfer function, so we're going to need these. Yeah, so we're good. So I need to close down this other window because I already got partway into this. So here's MATLAB. You've seen this interface, right? Everybody say yes. We did this in 227, 10 years ago. So you launch MATLAB, and then you click on this thing that says Simulink. And you say blank model. And you get this blank page. You can see that, right? Because I'm sharing everything I do now. And we can start dragging blocks into this thing that do stuff. They do great stuff. So I'm going to show you the great stuff it can do. You go to this library browser, and those are the blocks that you want. And we're doing continuous time systems. So we want this block that's called a transfer function. So that's where we're going to enter the U of S over delta E of S transfer function. And then I'm going to feed it the elevator input. And then I'm going to get the U as an output. So everybody caught up? I know the software is always hard to track. So I launched MATLAB. And then in the middle of the screen, there's a button that says Simulink. And then I chose a blank model. And then I chose the library browser because it shows you all the boxes that you can put in. I'm going to leave this over here. And I'm just going to click on this and highlight it and then drag it over here and pop it into my Simulink model. And it's real small, so I'm going to make it bigger. Then I'm going to double click on it, and it's going to allow me to put in the numerator and denominator polynomials. So going back to that sheet with all those polynomials on there for the transfer functions, I'm just going to read off the numbers that we calculated or that he calculated for us. Let me double check, make sure I'm on track here. So these are the numbers that are the coefficients. And because there's 3 of them there, that means it's a second order polynomial to MATLAB. Again, this is just an array, but because I'm putting it into this numerator coefficients array, it's going to say, okay, that's a polynomial in the numerator. And then I do the same thing in the denominator. I just type in the denominator coefficients, and that's going to be that same polynomial that we've been working with all the time. And so that's the denominator polynomial. It's 1, 2, 3, 4, 5 coefficients. So it's that 4th order polynomial. And again, you just type it in an array in MATLAB, and it knows that it's a polynomial because that's there. So that's how I entered that transfer function. And I'm going to copy this into the paste buffer because we're going to need it again 2 more times. So I'm going to Control-C that. And it says, oh, okay, I've given up trying to display the polynomial in here, unless you drag this out bigger. Oh, in fact, I'm going to even cheat worse than that. I'm just going to copy this whole block. Copy. Paste. There's another block, and I'm going to double click. And then the denominator polynomial is already there. I just need to change the numerator, because this is the alpha transfer function.
We didn't calculate the denominator, right?
What do you mean?
The denominator polynomial, where did you get that?
That's the one that we calculated, A1, B1, C1, D1, E1. And then the other ones we did not calculate. We got it from that same page. Let's see, where am I? Minus 88.577 minus 79.298. I think I've got that right. Double check. So it's got 4 coefficients, so it's minus 42 s to the third, minus 11939 s squared, minus 88 point blah blah s, and then there's the constant term. Okay, I hope that's good. Again, because I cut and pasted, the denominator stays there. So there's my other transfer function. I still have that block in my paste buffer, so there it is again. Stick it down here, edit the numerator polynomial. And this will be our theta to elevator transfer function. I suppose somebody that might have that page handy could double check my numbers. Is anybody doing that by any chance? So far, so good? All right, good deal. Thank you. All right, so we have our transfer function blocks in there. And now we got to fix up the input. So the elevator is going to go in. So I'm going to go back to my library browser. And I'm going to go sources, because that's inputs. Sources and sinks. Sinks are outputs. Sources are inputs. So I'm going to put in, and not a constant, I'm looking for a step. Look here, you can do a ramp input. Those should sound familiar from controls, right? Step, ramp, and there should be a parabolic input here. So I'm going to create a step input. I'll put it over here. And if we edit this block, we can tell it at time equal 1, it's going to step up from 0 to 1. And now I'm trying to remember what, I don't want to put in 1 radian. Actually, we're going to do this in degrees. So that might be okay. Let's do 1 degree elevator input, because I'm going to convert to radians. But if I do that, then the airplane is just going to start pitching up. So I'm going to step up with the elevator and then immediately step back down real quick. So I'm going to copy this block, create another step, edit this, and I'm going to go from 1. No, I'm not. I'm going to go from 0 to 1. We're good. And we're going to do this at 2 seconds. So this is going to go up to 1 at 1 second, and this is going to go up to 1 at 2 seconds. And then I'm going to subtract 1 from the other so that I get a pulse. So I need math operations. So you can see you have to poke around in this thing to find the add block that we need. And I'm going to change the plus plus to a plus minus so that this goes in at 1 second. And then this comes in at 2 seconds and knocks it back out. And then I'm going to go to a multiplier block. It's called a gain block. Send that in there. And this is where I'm going to turn my degrees into radians because we need radians going in. So there's degrees to radians. And that's my elevator input to the system. And I'm right-clicking on these signals to grab the extra branch that's going down like that. And the nice thing about MATLAB, how are we doing on time? We're almost out of time. I'll show you this, then we'll finish this next time. The sinks are places where you can look at the output, and the nice thing you can do is you can put a scope that's really just a plot of the function or the variable as a function of time. And I want to see what my elevator looks like. So I'm going to put my elevator into this scope. No, I'm going to do it in degrees. And so I probably should, well, that's elevators in degrees. So there's my scope. All right, we need to finish this next time because I'm going to put scopes over here for each of these so we can track those as well. But we'll do that next time.